The webinar will begin now.
Good morning, everybody. Good afternoon. Hello to, I see here people from Hong Kong, Germany, Romania. Just a little sound test. So is everybody hearing me? If yes, then you can use the chat box to type in some text. We will use this chat in order to solve technical problems. Perfect. Thank you. So let's start the business today. So once again, hello everybody, and thank you for joining the webinar today. In the past webinar, we introduced the Smart Interactive User Experience, a software upgrade which gives users guided instructions and interactive feedback. In the webinar today, we will introduce a new laser source which provides widest tuning range from 550 wave numbers up to 7,000 wave numbers, and also supports both SNOM and Afm-Ir technologies. Both technologies, SNOM and Afm-Ir, have been demonstrated live in one of our past webinars, available on demand. To access our on-demand webinars, visit the NeaSpec webpage and select the Education tab. To outline the webinar today, we will start with a brief history of light sources coupled with NeaSpec microscope. We will move then to present few potential applications enabled by this new laser source. And we will conclude with our guest speaker, Magnus Jonsson, from the Royal Institute of Technology in Stockholm. Magnus will present corrosion studies on metal oxides applications, which is strongly boosted by this new laser source. At the end, we will have Q&A sessions. You can submit your questions at any time following the tab on the right side. For maximum interactive experience, all questions are public, and you can use the vote button over here. So if you are using now the chat, that's okay for chatting between us, but questions, please hand it over to the questions tab. Okay, so before we start with recent worldwide unique IR nanoscopy results, let's start first with a brief history of light sources coupled with NeaSpec microscopes. The standard light source utilized by an FTIR microscope is based on thermal emission and exhibits a spectral range covering 400 to 4,000 wave numbers. This spectral range relates to the black body radiation emitted by a hot wire. Simply put, the FTIR microscopes are equipped with a light source which resembles a common light bulb like this one. For this reason, the temperature of such sources are rather limited to about 1,000 degrees, which limits also the spectral irradiance. Another limitation of this source is the coherence property. What I mean is how much light can we really focus into a very small spot and can be used for microscopy studies. This is the reason why the graph on the left is normalized to spectral irradiance. This graph plots how much light can we focus on each squared centimeter at each wave number. And for the FTIR thermal source, these values range around 10 to the minus 4. Now, let's pick another light source, IR synchrotron beamlines. These light sources have been also successfully coupled with several NeaSpec microscopes worldwide. The spectral irradiance of the IR synchrotron in Berkeley, depicted here in the picture on the right, is between 0.1 and 1. This light source is, of course, preferred when comparing with the FTIR sources due to its larger spectral irradiance. It is, however, not available to anyone. Such a synchrotron is tens of meters in diameter and also might not fit into any lab. Several IR synchrotrons are equipped with near-spec microscopes and also accept proposals. So if you want to go that way, write me an email and I will put you in contact with the beamline scientists which are near your location. Alternatively, you might consider an IR light source. The graph on the left shows two options. 700 wave numbers broad DFG lasers, as used in the Nano later publication of Florian Hood, former member of Rainer Hillenbrand, or you might go for an Opio light source as used for the Journal of Physical Chemistry later, published by Xiaoji Xu from Marcus Raschke Group. At this point, I would like to really congratulate all researchers who are using nano-FTIR technology independent on the light source. The publication list is just too large to present it here. The reason I chose those 4 publications is because of this self-explaining graph inspired by the PNAS publication of Hans Bechtel. In this graph, it's very obviously that the more light you can focus on the tip, the narrow becomes the spectrum. And this is the challenge we have to face, how to focus enough light and still have the whole IR spectral range covered. Both the DFG laser and the Opio laser can be also tuned to other frequencies. For the DFG laser, 2, sometimes 3 of such tuning ranges are enough to cover 650 to 2200 wave numbers. A Opio laser source can be tuned even beyond that spectral region. It requires, however, more than 10 such tunings. A much higher spectral irradiance exhibits a single-line laser, like a QCL. Even more, such a single-line laser is tunable as well, covering a typical spectral range of 800 to 1800 wave numbers. Even if the tuning range is small, the tuning speed is very fast and enables you to perform spectroscopy at specific points on your sample. So what we need is a combination between the large spectral coverage of the Opio laser and the fast tuning speed of the QCL. This is one of the most questions we receive from you. Which laser is best for my application? Should I use a QCL laser? Or maybe a DFG laser, it's a better choice. The standard answer you get from us is, depends on your applications. And allow me to give you a glance on why this question requires a tailored discussion, and the answer is complex. For instance, if you follow the graph on the right, you might want to perform fast images. Other researchers are interested in fast spectroscopy or hyperspectral imaging. Even more, we have researchers who are using complementary technologies such as SNOM, Afm-Ir, nano-FTIR. Sometimes spectral coverage is an issue, and of course, always price is a problem. To summarize, doesn't matter if you have a specific application in mind, you run a user facility, or maybe you have a broad collaboration network, just contact us and together we'll find the light source which best suits your topic. In other words, you bring a sample to us, you develop a proposal together with us, you have a research idea and come to us, and together we find out which laser, which application, which product configuration best suits your requirements. This webinar, to come back to the light sources, is focused on introducing the new Opio laser source. For a live demonstration of QCLs and DFG lasers, you can watch one of our on-demand webinars available at our website. In the Nano Afm-Ir live demonstration, we use the DFG laser, while in the SNOM and tapping Afm-Ir demonstration, we use the QCL laser. The Opio laser source expands the spectral coverage of the QCL and DFG laser on both sides of the spectrum. For your convenience, I plot on the left side the individual spectral coverage and added on the right side the spectral coverage graph. One note here, the QCL laser can be customized to cover also other spectral range. This is against additional cost, of course. Now, for this webinar today, I selected applications to explore the potential in both of these additional spectral regions, at the lower frequency, but also the higher frequency. Let me start with the antenna applications, which is one of the popular study within the NeoSpec users, both plasmonics and metallic antenna applications. For an updated list of references, please follow the publication page on our NeoSpec website. To come back to the plasmonic and metallic antenna application, the Opio laser source adds a huge advantage to this particular field. With this laser, you can use, for instance, excitation wavelengths which were not possible to access before. For instance, the 700 wave number frequency, where the antenna size needs to be only 350 nanometers, which is 7 times smaller than the antenna used in the publication from Alonso Gonzalez, shown here. Which also means that you can now access studies at sub-micrometer systems. To conclude, this laser opens now the door towards nano antennas, and why not nano metamaterials. In another recent study published this summer by Konstantin Wirth from the group of Thomas Taubner, such an Opio laser has been used to study the electronic properties of bilayer graphene. Until now, most of the graphene studies were concentrated in the spectral region around 1,000 wave numbers. That's still possible to realize with the laser that we'll introduce today. The laser, however, this laser adds the possibility to run studies at wave numbers outside the QCL range. Wave numbers which are important for bilayer and multilayer graphene, as shown in this recent publication over here. Another popular topic, as proven by the large publication list, is the study of boron nitride and related hybrid 2D stacks. In all those studies, the fast IR images were performed at wave numbers covered by the QCL laser. In other words, somewhere between 13 and 15 wave numbers. The new Opio laser opens now the possibility to expand those studies below 800 wave numbers and access, for instance, the type 1 boron nitride band. Once again, who is interested in the publication record, please visit our website and go to the References tab. One more application I would like to present before handing over to Magnus is another very broad spreaded research field. There are actually two, polymers and life science. Those two application fields using QCL or DFT lasers have been already presented in one of our past webinars available on demand on our website. What I want to stress here is that the new Opio laser enables both imaging at specific frequency and spectroscopy at any point on the image over the whole spectral range. In this example, we have a PS-PVAC polymer composite imaged at the frequency outside the QCL range at 697 wave numbers, which is, by the way, the strongest absorption band of PS. Worldwide first measurement at that frequency here. Even more, in only 4 seconds, you can get this 1000 wave number spectra by selecting either PS or PVAC region. Here we choose the 800 to 1800 wave numbers just to compare it with the typical spectral region of the QCL. I would like to summarize with a list of advantages born out of this unique technological marriage: an E-aspect microscope and the Opio laser source. First of all, the laser we introduced today covers the widest tuning range from 550 to 7,000 wave numbers, and sometimes even beyond that. See this image at 540 wave numbers. The tuning speed is also very fast and allows mapping a different frequency, but also recording of spectra at specific points. A second advantage is the narrow line width, which is less than 4 wave numbers, as required for the 2D materials. In this example, we have a boron nitride sample measured at 1480 wave numbers, and the line profile showing the long phonon polariton propagation, which is characteristic for this material. Last advantage of this laser source and the marriage with the E-aspect microscope is the compatibility with both SNOM and Afm-Ir technologies. Now I would like to introduce our guest speaker, Professor Magnus Jonsson from the Division of Surface Chemistry and Corrosion Science from the Royal Institute of Technology in Stockholm. Magnus' research topics are fairly broad, and let me invite him on the stage. I see, Magnus, you are already there. Thank you for joining this webinar today, and we are looking forward to see what results have been produced with this laser. Magnus, the stage is yours. Let me put also the presentation.
Thank you. Can you hear me? Do you hear me, Sergio?
Yes, clear.
Okay, very good. So thank you very much, Sergio, for letting me present our latest data on nanoscale studies of atmospheric corrosion. In my lab, we use nano-FTIR spectroscopy in a number of different fields, for example, in studies of nanocellulose and plant cell walls. But today I want to focus on the atmospheric corrosion of copper surfaces and how we can benefit from the new laser that Sergio has introduced today. If you have any questions to me later on, you can just send me a mail to magnusj@kth.se. The reason we study copper is that it is a metal that has been used in a lot of different applications in industry. You can, for example, see it on old church roofs. However, a problem with copper is that it corrodes in a number of different environments. And in order to really understand the corrosion, we need to study it on the nano level. So that's why we are using nano-FTIR spectroscopy. If you start to look at the macro scale, this is a corroded piece of copper. It's 2 by 2 centimeter large. It has been exposed to 80% relative humidity and formic acid, which kind of simulates a typical indoor environment. And it is clearly seen on this photograph that the copper corrosion is inhomogeneous. If you start to look at the whole piece essentially, and we take an infrared reflection absorption spectrum, also called grazing incidence IR, we can see that there are 2 corrosion products that are formed on our surface. We have the copper oxide, the cuprite, at 650 wave numbers. We have the copper hydroxy formate at 1600 wave numbers, and that also gives rise to a peak at 3570 wave numbers. This OH stretching vibration we look at there. So those are the products we look at. And then we zoom in a bit. We look a little bit closer. We look at this small ring here. So inside this ring, you can see that we have a kind of a brown-orange sea, and in this sea, we have some blue islands. And this scale bar is 20 micron. This is a light optical image. And this sample has been exposed for 72 hours to this model indoor atmosphere. And then we'll take a little bit closer look with IR spectroscopy. We use a conventional IR microscope, and we study an area that is 50 by 50 micrometers. And here you can see that the IR spectrum kind of resembles the one of the whole surface. We have a copper oxide peak, and we have these 2 strong copper hydroxy formate peaks. Now, these 2 peaks down here also correspond to copper hydroxy formate. However, to really understand this corrosion process, as I said, we need to study it on the nano level. So that's why we also started to perform studies with a nano FT-IR spectroscopy. And to the left, you can see an AFM image. It's 1 by 1 micron. And you can also see some spectra that we have taken. We have taken 2 spectra, A and B, in the region where the cuprite, the copper oxide, is seen. And this is seen as 650 wave numbers, really at the cutoff frequency at our femtosecond broadband laser. So it's a difficult peak to detect. If we look in another spectral region, we have 3 spectra, C, D, and E. You can see C here, it's a blue one, that's a large particle, and it obviously contains copper hydroxy formate. D, we have down here the orange one. It gives a little bit smaller peak, but it still consists of copper hydroxy formate. And then we have the particle E up here, that you see that it's almost no intensity in this region, meaning that that particle consists of something else. We can also study with another broadband laser, the upper frequency region, and here we can probe the OH vibration of the copper hydroxy formate at 3570 wave numbers. So we have then 2 different ways of probing these copper hydroxy formate molecules at the nanoscale. So we can identify them there. And now I will come to this nanoscale imaging that we have used this new laser for. And first I would like to show an AFM topography map of our corroded copper surface. So this is 10 by 10 micron. And you can see that the surface consists of some larger flakes all over. And then we also have areas that only contains small gray particles in a black sea. And the roughness is quite high, some hundreds of nanometers. And if you zoom in, this red square in the middle, you can see again in more detail that we have some larger particles, the white ones with a height of 100-200 nanometers. And we also have these smaller particles in the Black Sea. So what we then have used this new laser to is to map these 2 corrosion products on the nanoscale. We map the copper oxide and we map the copper hydroxy formate. So if we start with the copper oxide, the cuprite, it has its maximum vibration at 648 wave numbers. So with this laser, it was taken an image. We have an amplitude image showing reflectivity of the surface. You can see that it's lower at these larger particles. And then we also have the optical phase image that more probes the IR absorption properties. And here red means a higher phase, meaning a more IR absorption. And we also have to the right the copper hydroxyformate. Here we tune this new laser to 1600 wave numbers, where the maximum vibration is for the copper hydroxyformate. Again, we have the optical amplitude. We can see that the reflectivity is lowest at the largest particles. And we also have this optical phase image, where you again can see that the higher IR absorption is found where we have these red areas. So we have then been able to separately map on the nanoscale the copper oxide corrosion product and the copper hydroxyformate corrosion product. And I also would like to zoom in on this 2x2 micron AFM topography image. Again, you can see at the top the amplitude, reflectivity images at 648 and 1600 wave numbers. But mostly I would like to focus on these lower images, which shows the phase, which is related to the IR absorption. And if you start to look at the cuprite, the CU20, the optical phase at 648 wave numbers, you can see that the maximum phase, the red areas, are found if you also look at the AFM topography images where we don't have the large particles. So it's more the small particles and where we have the black sea. If we instead look at the image of the copper hydroxyformate acquired at 1600 wave numbers, you can see that the highest phase, the higher IR absorption, occurs at these red areas, and that is exactly, if you compare with the AFM topography images, where we have these larger particles. So we can draw the conclusion by these two images that the copper hydroxyformate particles, they are the big ones in this AFM topography area, and the cuprite, the copper oxide, is localized more in these lower areas with these small particles. So with this new laser, we were able then to expand our studies and independently map where we have these two types of corrosion product, the copper oxide and the copper hydroxyformate. So for us, it has really been a benefit to, additionally from mapping only the copper hydroxyformate, we could also map this lower frequency 648 wave numbers. This work, the initial work in this presentation, was done by Dr. Weijie Zhao, my PhD student who graduated some weeks ago. It was also collaboration with Professor Christopher Legraf at KTH, and then some of the images were taken by a former NEASPEC co-worker, Dr. Miriam Böhmler, now at Bitech. And then I was very grateful to Adrian Cernescu and to Klaus Reckmeyer at Attricube, who were taking these last images with the new laser. And also the China Scholarship Council and the Olle Enquist Foundation for financing. So thank you very much, Sergio, for letting me present this data.
Thank you, Magnus. A wonderful work over here. There is already a question related to you, or let's put it the other way. It looks like somebody wants to collaborate with you, so it's asking for your email address. We will come back to this question in a second. Before that, and before starting the Q&A sessions, let me just share another slide. Two more exotic applications here, functional oxides and silicate minerals have been measured just recently with this microscope laser combination. And what I want to do is an announcement for you, for everybody here. We are open for collaboration, so let's team together. You bring a sample or an idea to us, and together we can increase the success rate of your next budget application. And what I will do now, I will put in the chat room a link where you can apply for collaboration with us. And the link is on the way. From now on, let me move to the next slide over here. So we will open the Q&A sessions. So from now on, if you have questions, please put them into the chat tab, into the question tab, not in the chat tab. And just to have a practice, an exercise on those steps, which are all on the right side of your screen. And there is also a poll step. So if you go to the poll step, I just submitted a poll, which you can vote all of you together. More precisely, you can answer a question, which is, how often do you submit grant proposals for budget application? It is more than 3 times a year, 1 to 3 times each year, once in every second year, or no budget application in the last 3 years. One hint, so if you vote on the polls, you can also get the results from everybody else. So I will be honest with you, personally, I didn't submit any budget application in the last year, so I'll also submit right now my vote. So we have already the voting over there, so please keep voting through the Q&A sections, and now we will move to the questions tab to start answering the questions. And Magnus, like I said, the first question, which is now online, it's from Richard. He wants to have your email address repeated, so your credentials. What we can do either probably.
Yes, I just typed my email in the chat. It's magnusj@kth.se.
Okay, then we're done with this question. The next one relates to the what's the price of the Opio laser and what is the irradiance compared to the QCL and the DFG laser. And to answer that question, let me go back to the slide I had before over here. So the spectral irradiance of the Opio laser, it's somewhere in between the QCL. Of course, the QCL being a single line laser, you can put as much power as you want on that line. While the DFG laser, it needs to spread all the power over larger spectral regions. So it's somewhere in between. Regarding the price, it's definitely an expensive laser compared to the QCL and the DFG. We can do such that after the webinar, my colleagues will contact you and will discuss directly, because it's depending also on the specific configuration and all the options that we have. Okay, so we are done with this question. Let's move to the next one. The next question is from, moving around, Tanver. Can we discuss about the experiment setup for the nano Afm-Ir laser? I would lovely do that. Let's see if we have a little bit more time at the end. What I'm encouraging you is to watch the live demonstration on Afm-Ir, which is available on our website. So there you have not only the presentation and experimental setup, what exactly do you need, but also some experiments done and a lot of questioning and answering. Let's move on to the next one. Gianfalco, what is the XYZ resolution of the instrument? That's actually a very good question. So let's put it this way. XY, it's always depending on the tip size. The standard tip size that we used in the presentation, that in the images that we showed in the presentation, range around 20 nanometers. So that will be the X and Y. In the Z range, depends on, first of all, on the technology. So you might use Afm-Ir, which is probing more volume, or taping Afm-Ir, which is more surface sensitive, or if you use SNOM and nano-FTIR, you can also play a little bit with the penetration depth by choosing a different tapping amplitude. So that's ranging, and the range is everything between 10 nanometers and, I don't know, 2 or several hundreds of nanometers. Like I said, PTE will give you more probing volume, while SNOM or tapping Afm-Ir, it's more surface sensitive. I hope the question was answered properly. Otherwise, you can start a new live question. Another question from Varun. Can we use the IR nanoscopy in the grazing mode for mapping regions in polymer thin films? Well, that's actually a very good question. And here I refer to one of our past webinars. I think it's the polymer science, where we had the introductory slide on the nano-FTIR. And for nano-FTIR, it turns out that you do not need to measure in different modes. So you get both the transmission-like experiment and the reflection in one run. It is a little bit going outside the topic of this webinar, but I will encourage you to watch the webinar on polymer science. We explain in detail how this works over there. Thank you, Varun, for this wonderful question. It's very good. Okay, let's move on to the next question from Christine. Thank you for watching the presentation as well. Is the new Opio compatible with the first version of NeoSNOM hardware and software? Well, that's a very good question. Well, to some extent, you can do experiments with the combination. I would, however, encourage you to upgrade to the newest generation microscopes. The main reason is that with the new generation microscopes, you get also the spectroscopy in a kind of a push-button manner. But not only that, if you really want to be convinced about the upgrade, I recommend you to watch the previous webinar where we introduced the smart interactive user experience that's based on the new software. And I believe you might be definitely contacted by my colleagues, because it's just too good to miss the features of the new generation microscopes. Thank you, Christiana, for that question. Okay, a lot of laser questions over here. Let me go for the next one. Is the new laser a combination of Opio and DFG module? I believe from the technical point of view, you have right. So let me explain what Opio and what DFG means. Opio, it's optical parameter oscillator. It's a laser where the beam goes several ways in the cavity, which means you are going through the crystal many times, and that for that reason the power that you get out of that kind of laser is much bigger. The DFG is difference frequency generation, which means you take two different lines, frequencies, and you build the difference out of them. And because it is much easier to build lasers in the visible or near IR spectral region, you would take those frequencies, and by making the difference, you will generate IR frequencies. To keep it short, yes, the new DFG laser has both components inside the Opio as a main source, and then a DFG to generate the final difference mixing in the IR. Thank you, Guanjun, for this wonderful question. Next one, it's from Maria. Very good question. So is the Opio used for pseudo-heterodyne detection module? Do you need to change the mirror modulation amplitude during the wave number tuning for spectroscopy? Two very good questions, and let me go to the proper slide over here. So what we refer to is this example here, or maybe the next slide, it's even better. So in ASNOM, we use the pseudo-heterodyne detection in order to measure both the phase and the amplitude of the sample. So here is the phase plotted. And indeed, when you want to move to a different wave number, you need to tailor the reference modulation of the detection module. The larger the wavelength, the more you need to modulate that mirror. That's, however, done automatically, and that started with the new generation software. I believe software 1.8, 1.7. That was also presented in one of our past ASNOM webinars, how this automatic relation between the modulation of the mirror and the frequency occurs. So if you, I don't know if you have a microscope which has that software, but if not, then let's get in contact and go together to see what solution is best for you. And the second related question from Maria was that what do we do when we tune the spectral range? So indeed, when you run a spectral IR spectral at a specific point, you need to tailor the modulation frequency for each wave numbers. But this is again done inside the microscope. You don't need to take care about those engineer things. Okay, let's move to the next question from Pablo. So here is needed a clarification. Is the same Opio laser used for both nanoimaging and nano-Afm-Ir? Okay, again, clear, short clarification ahead. A nano-Afm-Ir, it's a technology which uses broadband light sources and works the same way like the Afm-Ir works. So you have a broad light source, you focus on the sample, and then you measure initially an interferogram, and then you transform it Fourier. That's why the name Fourier transform IR. Now, the Opio laser that we used here in these examples, it's very narrow. It's like shown in the slide over here. The line width is below 4 wave numbers. To keep it shortly, you might use nano-Afm-Ir, but being the narrow weight so small, it doesn't make too much sense to use that. So therefore, the data that we presented here are either coming from the ASNOM technology or the tapping Afm-Ir technology. 2 examples here. Hope that I answer your question entirely. Thank you for the question, Pablo. Next question from Vyron. Very good question. It is possible to run the nano-Afm-Ir in a liquid environment. There are studies out there using liquid environment, and ASNOM nano-Afm-Ir were related sub-micrometer scale methods. The last, I don't know if you are in emailing list of the Journal Club. Last Journal Club just last week presented a related topic, nano aquarium, where live cells were measured with this technology. And let's do it this way. I will send you the Journal Club also to you. Sorry for missing you. And at the same time, if you want to have, let's say, a liquid cell, that's possible as well. There are, meanwhile, also some publications in that direction, both on polymers, but also on 2D materials. The way how you do the liquid measurement is that you are not coming from the top and exciting the sample, but rather you need to come from below, because you do not want to go with the IR light through the liquid. And the most or the whole IR light will be then absorbed. Now with this laser, since it's much more powerful, I see a lot of advantages in combining with the liquid cell, with the liquid environment. So how about me or my colleague will contact you after the webinar and discuss exactly what are the requirements there. Okay, we have a next question from Frankie. Is there any tuning speed difference between Opio and the QCL for the Afm-Ir application? Let's take this question. Sure. Other band of equipment emphasizes that QCL can acquire a spectrum within 5 seconds, but Opio need 5 minutes. Very good question. Indeed, if you look on the market at the Opio that are available there, the tuning, and that's the problem that I put it at the beginning of the webinar, the tuning speed of Opio or DFG is rather within minutes. It's not seconds. The light source that we introduce here, this Opio, can be tuned within seconds. And I showed you an example in the previous slide. Let's go back to that one. Here, this is 800 to 1800 wave number spectral coverage within only 4 seconds. So that's making comparable to QCL tuning speeds. And if you want to experience how fast can a QCL be tuned, I would recommend to watch our live demonstration, either the SNOM live demonstration or the tapping Afm-Ir live demonstration. Hope that the answer was answered. Otherwise, we can also discuss after the webinar in more details. Thank you, Frankie, for the question. Now, the next question is from Mikhail. Very good technical question. What is the signal noise of the new Opio? Okay, so let's step back once and define what is the signal to noise. So usually you measure the signal to noise by the ratio between the signal and the noise, and then of course depends also on the material that you are measuring. One of the slides presented graphene monolayers, and of course graphene monolayer might be challenging to measure compared to polymer, which is 20 nanometer thick or even larger. Now, if you compare the previous generation OPOs with this OPO on the same material using the same microscopes, also between the microscopes might be a difference. So if you take a microscope from NIASPEC and compare it with other microscopes which might be available on the market, you would see also a huge difference. So let's take the best microscope on the market from NIASPEC and use a standard sample. And if you compare the two OPOs, we did this in the past. I would say that the new Opio showed even better signal to noise, by far much better than 20%. So it's in the noise, it's in the range of just few percent. Otherwise, you will not get images qualities like that. On the other side, so why is that? First of all, it's because we have the spectral range of that laser. It's much narrower, so you can focus much more power on the specific wave vibration over here. But also, it's that the light source, it's much more powerful compared to per each wave number compared to other Opios. So that might be the reason between them. Okay, thank you, Mikhail, for the question. I see no further questions. Let me scroll up. No, there is one coming from Andreas. Can we compare the advantages and disadvantages of recording spectra with the new Opio laser in the and the imaging with the DFG laser? So the way how we should proceed here in order to answer clearly that question is the following. Let me go to the proper slide. Here. So when you choose for a light source for a new microscope, you contact us, and what we do is we choose one or the other representative samples from your research area, and we test it with several lasers. Sometimes the DFG is the better options for some application or some samples. Sometimes there is the QCL laser. And of course, even if seems much better choice, the new Opio laser, always the price might make the proposal that you are submitting more difficult. And for that reason, I would not exclude any lasers from the discussion. In fact, in our customers, in our factories, we combine not only these three lasers, but many more other lasers beyond that. Lasers which are much broader than the DFG laser and emitting somewhere in the 2 microns to 4 or 5 micrometer range. Lasers which are single line frequency and emits in the visible terahertz. It's a spectral region which is also welcomed and combined with our microscopes. So depending on your applications, the best way is to contact us. We settle up a meeting together and define what combination is best for you. Thank you, Andreas, for your questions. I'm done. Next question from Gergerly. Let me put it on the screen. What is the exact line width of the Opio laser? And if that line width defines the spectral resolution? Well, let's answer step by step.